All right, so today we will be talking about halo2 ECC, which is a library using the halo2 proving system to provide configurable prover verifier tradeoff and provide a library for some common elliptic curve operations in snarks. So these are operations that are common in many cryptographic applications, including addition, doubling, multiscalar multiplication, and the optimal 8 pairing, as well as ECDSA signature verification. And we do it in a way where it's easy to change what curve you're using. So any Weierstrass curve is possible, including BN254 and segp 256 K1. And to give some motivation of where these circuits can be used, to give some motivation of where these circuits will be used, ECDSA needs no introduction. But another one is that we are using the KZG-based halo2 proving system, and that currently does not have recursion enabled. But to recursively verify such a proof, there's a bunch of hashing involved, and then a lot of elliptic curve operations. One big part is using these multiscalar multiplications on KZG commitments, and the other part is the pairing check. So using our library, we are actively working on enabling recursion in this system. To give some sense about the current performance of our circuits and what it means to have a prover verifier tradeoff, we give some benchmarks. So this one is for the optimal 8 pairing in BN254. So basically, there's a bunch of things that you can configure in the proving system to give different performance benchmarks. So the first few columns are all specific to halo2, but the main thing is the last 2 columns, which is prover time and proof size. So as the table goes down, the proof size increases, which also means the verification cost, for example, on-chain increases, both due to call data and some other reasons. And so in this table, you can see that as the verifying cost goes up, for a while, the proving time is going to decrease. But then, so this does not go on forever, and at some point, like the proving time will reach, I guess, optimum value. So for optimal 8 pairing, we go from 250 seconds down to 300 seconds. And this is on a MacBook Air using the M1 chip. So strangely, in halo2 right now, it turns out that the M1 chip is actually faster than using like a 32-core machine, AWS machine. So we don't really know why that is the case. And so this is our circuits are not fully optimized, so these numbers are subject to change. And so just to give some idea of the previous columns, so they're specific to halo2, but basically to get the proof size down, we decrease the number of rows, and that means increasing the number of columns. And we also use some lookups, but in order to get that to fit into the number of rows we have, the lookups have to change as well. And here is a similar table for ECDSA for segp. And so this is a smaller circuit, but it follows the same pattern where proof sizes go up, and then you reach some optimum or lowest proving value, and then it goes up again. And so for us here, it's going from 15 seconds down to 4.8 seconds. So to give some idea about how we designed this library, I'm going to give the fastest crash course on halo2 possible. So it uses the Planckish arithmetization system, which basically means that you're filling in a matrix with values, where the matrix in halo2, it has to have 2 to the k rows and then some number of columns. And so there are some different types of columns represented by colors, and these give different performance implications. And just to give them some names, so there's instance columns, which correspond to some public inputs, advice columns, which correspond to basically all of the private values in your computation, and then fixed columns, which contain any like constant numbers that you want to use in the computation. And to actually make this like some ZK circuit, there are some core primitives that are available. So the main one is custom constraints, or also known as custom gates, to make sure that this number satisfies some properties. So for Planckish arithmetization, there are lookup arguments, which basically say that you can check that some values are in some table. And finally, you can enforce that certain cells are equal. And so in this, so that's the system. And to talk about proof or verifier tradeoff, you need to have some rough mental model of like what matters and what corresponds to what. So for the prover, they work with each column as some polynomial. And then on this polynomial, they'll need to do some operations like fast Fourier transform and elliptic curve operations like MSM, which is multiscalar multiplication. And these take different amounts of time, and there's different parallelizations available. But roughly speaking, so more rows and also more columns that have lookup arguments enabled means that there will be a longer proving time. Meanwhile, more columns will mean that it'll be a larger proof size. And then for the verifier, they'll receive the columns basically as KZG commitments, which are just some elliptic curve points. And there, the cost model is basically that if you have more columns and also more custom gates, this means that there will be a higher verifier gas cost. But roughly speaking, basically, your computation will have some number of cells, and then if you can configure it, then the more rows there are and the narrower it is, that means that that has higher prover cost and lower verifier cost. And the wider it is and like the shorter it is, that means it has lower prover cost but higher verifier cost. So with that, to give like the simplest starting point of our circuit design, we start in the cheap verifying setting, which is also the most constrained. So we do like the least of everything possible, meaning we have just one advice column, and then 4 fixed columns, which have some specific names. So there's one like lookup table, 1 column for constant values, and then 2 columns for what are called selectors. And then there's just one single custom gate, which you can enable at any point in the single advice column. So if you have like 4 contiguous cells, A, B, C, D, the custom gate is just saying that A plus B times C is equal to D. So it's very similar to like R1CS. You can add and multiply. But so in like a more standard Planck system, the gates would be horizontal, and you would do something similar to this. But actually, this cheap verifying setting with the vertical gates has some advantages, which is that you can overlap. So I'll explain with an example. So one thing that we actually do a lot in our circuits is just computing dot products of 2 vectors. And so here, let's say we want to take a dot product of 1, 2, and 3, 4. So first, you just compute like, oh, OK, I think I actually did not compute the right thing. So let's say, I guess we are computing the dot product of 1, 3, and 2, 4. But OK, so first, like let's say you're computing 1 times 2. So this is just like, there's no addition. So you start out with 0. And then I put it in the blue because this is a constant value. And then, so it's 0 plus 1 times 2, and is equal to 2. So that's just one gate. But now you want to add it to 3 times 4. And you can overlap it by, so you already have the result of 1 times 2. And now you just add 3 times 4 to it. And this shares 1 cell in the middle. Whereas in some other circuit designs, you would have to just do them separately. And then you need to like say that the result of the first computation is like equal to the starting point of the second computation. So this overlap like on larger vectors of size n, so you would only use 3n plus 1 cells instead of 4n cells if you didn't have the overlap. And it turns out that we did like some benchmarking. There are just so many dot products in many of these math operations that this like 25% saving is actually quite significant.
All right, so now I'll talk a little bit more about how we can transition from this very cheap to verify vertical gate to actually see a prover verifier trade-off in practice. First, like the motivation for this is that if you look at some Stark-based systems like Plonky2, there's a very natural trade-off between prover cost and proof size and verifier cost. And of course, they have large proof size corresponding to fast to proof and small proof size corresponding to slow to proof. But it comes from a very different place. There are probably many people in the audience who know this much better than I do, but it roughly corresponds to varying the number of Merkle paths that you ask for in the Fry argument. And so what we want to do for snarks is to have a similarly configurable or programmable way of implementing a prover verifier trade-off. OK, so in these plots, you can see the trade-off that we can plot for the optimal 8 pairing on your left and the ECDSA verification on your right. So you can see that as we take the single column setting, which is the far left data point in each plot, the proving time starts off pretty high. And as we increase the proof size to around 10 kilobytes, we reach some sort of minimum. And then we plateau as we increase the number of columns to get pretty large proof sizes. And so we're able to do this by reshaping our circuits in a slightly programmatic way, which I'll now tell you about. So we first started off with the most naive possible way of reshaping a circuit. So roughly speaking, if you have a very tall and skinny circuit, how could you make it wide? Well, the first thing you could think of is just cut it up and reshape it. So in this circuit, you can see we take the first 4 rows, and we cut off the top of that circuit, and we just put it horizontally with the bottom 5 rows of the circuit. So then we have a reshaped circuit with only 5 rows instead of 9. So this is a bit naive, and frankly, we want to do a little bit better. So what we did is we implemented something which may or may not be called a layouter in Halo2, but it's a pseudo-layouter. And what that does is every time we want to lay down gates in a region, we do a greedy allocation across our available advice columns. So what that means is that if we have a length 4 vertical region, well, we'll put it in the first column. And then if we have a length 2 one, we choose the next empty columns, since that is 0 cells allocated already. If we now put in a length 3 region, we'll again put it in an empty column. And then we can finish off by eventually densely packing this table. And so in this way, we're able to obtain circuits that allocate regions across columns very evenly. Now, there's still some discrepancy, which maybe we could solve some optimization problem to improve. But we observed in practice this doesn't matter too much. The final thing we did to actually see this prover verifier trade-off beyond the naive reshaping of cells to columns is by sharing lookup arguments. So previously, we took our lookup argument and simply enabled it across all columns. And what we realized is that this actually adds quite a bit of overhead for the prover. We think it's roughly equivalent to 2 extra columns for every lookup enablement. So one optimization we implemented is to only have 1 column with lookups enabled. And anytime we want to look up a cell for a range check, we simply copy it to our special lookup column and do the lookup there. Surprisingly, this actually reduced our proving times by around 50% across the board. So we'd strongly recommend this optimization in essentially any circuit. OK, so in summary, our library supports some of the basic elliptic curve operations. We can do pairing in 30 seconds right now, ECDSA signature verification in a little bit under 5 seconds right now, and we can do this configurable prover verifier trade-off. This library is under active development, so we're in the process of adding some partial automation for introducing custom gates. So far, we've only used this pretty dumb A plus B times C equals D gate, but we're recently realizing that introducing some custom gates can hopefully allow us to push the prover-verifier trade-off more. So at present, our fastest to prove circuits can use roughly 50 to 70 columns, but we're hoping that with more custom gates, we can maybe push that a little bit further. On a separate direction, as Jonathan mentioned, we're currently benchmarking on his MacBook Air, which we somehow feel is not the computing platform of the future. But if you work at Amazon, you may be embarrassed to see that your servers are somehow worse. But we are looking at the Amazon's next level offering of the GPU, and we're hoping that we can see a lot of improvements there. And we're excited to see what applications we can enable with those two combined. So that's it, and we're happy to take any questions.
So the 30 seconds is the proving time. What's the verification time?
So the question is, what's the verification time for all of these? And the answer is, we don't really know. Or we don't have good benchmarks for a couple reasons. One is that we are targeting on-chain verification, and the on-chain verifiers are kind of in a slightly unstable state. So we're looking to actively benchmark that.
I see. So even on your Mac, on the Mac, we don't know what the verification time is?
We just did not benchmark. But
Okay.
Yeah, it would be possible to benchmark those.
Okay. And then I just wanted to confirm, this is still using field emulation, or are you able to use native fields?
Yes, this is using non-native fields.
Non-native fields, yeah. It's very cool, very nice.
So I wanted to ask you about, so basically what you're doing is you have one long row and you kind of split it into multiple columns. And like, I want to ask you about the trade-off. With Grad 16, we have this really simple way to reason about the total number of rows that we can include. It's basically like 2 to the 28 rows. And I want to ask you about like, what is the trade-off when we're moving to multiple columns? Like, what is the maximum circuit size?
I see. So the question is, what's the maximum circuit size with multiple columns? I think it's just the same number of rows. So the total number of cells would be like 2 to the 28 times your number of columns.
Okay, cool. And like the degree of the custom constraint, does that affect the total? That's independent.
That's independent.
Okay, cool. Thank you.
Well,
It affects the proving cost, but it's independent of like this maximum.
Okay, it affects the proving cost, but also the verifier cost, right?
yeah.
Yes.
Yeah.
Okay, cool. Maybe I'll ask you more about that later.
Yeah.
Thank you.
Sounds good.
On your prover verifier table, trade-off table, why do you think that beyond a certain proof size we stop seeing proving time improvements? Like, why do you plateau?
Yeah, so we need to do some more serious or involved analytics on this. But one hypothesis is that actually as the number increases, there's some like just polynomial operations that start to dominate over any like FFT or MSMs. And so that part, it could just be that that part it's not parallelized yet, and it could be parallelized. But right now, like I guess in these plots, like once you have too many columns, like that starts to dominate, and like there's nothing you can do about that.
Thank you.
Yeah, just to add on to that, I think one phenomenon we observed is that it's very hard to isolate where the bottleneck is in the prover. Like it could be that some part of the specific proving system you're using, the implementation is not optimized as well as some other part, and that actually changes the bottleneck.
Yeah, we need better metrics. We need like flame graphs. Yeah.
Bunch of questions on the Twitter feed. Check out the Twitter feed, guys. So a grand wizard says, Yi and Jonathan, how do you prioritize which elliptic curves to implement? I don't know how many of these are going to be troll, but I'll ask all of them.
Yeah, I think we chose these just as pretty good benchmarks, and also because we're interested in targeting recursion. To add a new elliptic curve is not actually that hard. We simply have to change a few constants in our files. So if you're interested in some other curve, definitely let us know. We're going to look into BLS 12381, but we're open to other curves as well.
A wizard asks, how does Halo2 compare to Plonky2 as a dev? Although I don't know if that's relevant to you guys.
We just haven't used Plonky2 enough to really
No, fair enough.
We are speaking with the Plonky2 devs to try to compare, but yeah, we don't know.
Cool. And then last question. For Yi, this is from a sorcerer. For Yi, why do rows but not columns contribute to the overall cost?
The reason is that for the prover, whoa, some real magic going on here. So the answer is rows and columns both contribute to the prover cost, but the columns are the size of the FFT and the MSM that you do for the KZG commitment. So of course, when you have more columns, then you're actually just having to do more of those operations in the prover. But somehow, when you do more of those smaller operations, it changes the total cost. And the second point is that if you have more columns, you can parallelize those operations more easily.
Cool. And yeah, people keep using the feed. Also, I don't think we have a lot of time for questions, so Yi and Jonathan can answer stuff asynchronously too if you post to the Twitter.
All right. Thanks so much, Yi and Jonathan.